So today's going to be a nice little simple video on some rotational dynamics. As many of you may know from basic physics or AP Physics 1, I is generally given by mr squared. And this would be for if you had some axis of rotation and you had this point mass that was r distance away, and you would calculate it if you have a mass m. What is its rotational inertia around this axis? You would use this equation. However, for those of you in AP Physics C, you'll probably understand that that previous I equals mr is a little basic, and it doesn't take into account shapes that have their mass spread out, like this cylinder here. So for the cylinder, the question is, how would we find this rotational inertia? What is I even equal to? So the first thing to understand is that I isn't really mr squared. It's more so the sum of all the individual dots of mass here. So you have all these point masses, and then their distance r away. So this one's r away, and then this one's maybe a different r away, but then you take that r squared. So this is where this comes from. You're basically assuming you have a bunch of those small point masses we were talking about at the beginning. You have a bunch of those 1m masses, and they're like some r away. So imagine you have a bunch of those, and it makes up a cylinder shape. And for those in AP Physics C, you'll know that this can just be turned into an integral, which is just the integral of r squared and a little bit dm, like how I was saying, it's just one tiny little dot of mass. It's supposed to be an infinitesimally small amount of mass, but obviously it doesn't work that way. It involves limits and all this more complicated stuff that doesn't need to be talked about. But we can use this handy formula to figure out what I is for a cylinder. So let's get right into it. So taking a look at our cylinder here, we can try and figure out what this r is. So looking back at our equation, we don't want to actually find r in terms of m. It's much more beneficial to find dm in terms of r. So we want this dm to be some sort of dr. And just remember that this dm represents a small, tiny little sliver or tiny mass point in the cylinder that we're trying to find. And we haven't defined it yet, and that's the important part, so we'll figure that out right now. But it's important to know that this r squared is easier just to stay as r squared. It's hard to figure out what radius is given a certain mass. If that's intuitive, I hope that is. So let's figure out what dm is. We want dm to be something that can easily be represented as a function of r. So this looks very similar to something you would learn in AP Calc, which is called the shell method. And you'll know that when you're taking shells of this cylinder, might be bringing back some bad memories for people. Take this shell right here, and the mass of this shell is equal to dr. So we're going to take a small little sliver, we'll call this dr, and if we unravel it, it looks like a rectangular prism where it has this depth dr. So dr is this. Its height is obviously h. We'll just call the whole cylinder's height h. We'll call it big H. And then this length that it is the circumference. So that's pi, or 2 pi. And then we'll say the radius that we're looking at. So at a certain sliver, we're going to call it little r. And this is important. So the whole volume of this slice volume is going to be equal to this 2 pi r h dr. So we'll take this volume and put it up there real quick. And the second part we're going to have to ask ourselves is what is dm? So if we're taking this to be an infinitesimally small little cylinder here, as you can see, we're gonna just tell ourselves, okay, the mass slice we're gonna use is 1 cylinder. So we're gonna say dm is equal to the mass of this unfolded cylinder we have. And we can find this pretty easily. We'll just state arbitrarily we have some density phi, p, we'll just go with p, some density p, and then times the volume, and that'll give us p density times the 2 pi RH dr. And this is a value you want to keep in mind. And so we know that this is equal to density times 2 pi RH dr. So plugging this into our integral expression, we're going to get I is equal to the bounds from some a to some b, because it's going to be a definite integral. It can't be indefinite. You have to have a certain ending radius and starting radius. And then it's r squared times this density times 2 pi RH dr. And now this is an integral we can solve. We're going to combine the r terms to get r cubed. And then this and this can come out as constants because we're not differentiating with respect to those. So we're going to get I is equal to density times 2 pi h from a to b r cubed dr. And now our next question is, what is a and what is b? So the first cylinder is just going to be the one that is literally the axis. So it's so thin, you might as well have it be the axis of rotation. So that's a radius of 0. So a is going to be 0. And then we're going to end with the largest possible cylinder, which is just the whole thing, right? So this is going to have a radius of big R, because we're going to call big R the actual radius of the cylinder. So instead of a certain area radius we're at as we're inching closer and closer to the edge, R is the literal radius of our entire cylinder here. So this is going to give us our final evaluation that we're going to need to solve, which is p times 2 pi h from 0 to big R of small r cubed dr. So just remember, this small r is a variable, this big R is an actual value. So bringing that expression up, we're going to solve. Remember, this is all constant, so we can pretty much ignore it for now. So we'll have 2 pi h density, and then this definite integral can be just solved as 1 over 4 r to the 4 evaluated from 0 to r. The 0 is not going to evaluate because this is, or it's going to evaluate to 0, so we don't need to subtract anything. So we end up getting 2 pi h times the density is equal to r to the 4th, big R to the 4, over 4. So now the question is, what is this? What is density, right? Because density is something that we can't just assume we know. But in reality, we don't know a value of it, but it can be found with stuff that's already in here. That's very helpful. So let's figure that out right now. So what is P? Well, density, as we know, is just mass over volume. So we're going to say it's mass of the entire cylinder over the volume of the entire cylinder. So we're going to write mass over what is the volume? Well, the volume is going to be pi r squared, big R squared actually. So it's going to be this area of the base. And then we're going to multiply this by the height. So this gives us volume. This is V. From here, we can plug in to the top. So remember that this is what I is equal to. So we know that I is equal to 2 pi h. We're going to input our P value here, so it's M, and then over pi r squared h. And then we have this 1 over 4 r to the 4th term here. We're going to do some canceling. The h's goes first, the pi goes, the 2 and the 4 brings us a half on the bottom, and the r squared brings us to an r squared on top. So that gives us our final answer of 1/2. So there's this 1/2 here, 1/2, the m here, m, and then r squared. So the I, or rotational inertia of a cylinder, is 1/2 mr squared. And that is our answer. Let's clean up this math a bit so it looks clear. And there we go. So if you're in AP Physics 1, you don't need to know this. This will be provided for you. You don't need to know why this works. Or you should, but you don't need to know in the exam. They'll tell you, and you don't need to memorize this. So if you're solving any of those rotational inertia problems where you have like torque is equal to I alpha, you just need to know that it's 1/2 in front of the mr squared. But if you're taking AP Physics C, you aren't necessarily asked to derive it, but you should know how the mass distribution affects rotational inertia. So general ideas of more spread out mass means a smaller I because it's more well distributed, and if you have more concentrated points of mass, then that's a little bit higher I, and then further radius is greater I, and then greater mass is greater I. So the AP is very focused on those types of relationships between variables, so you should know how to do that. Other than that, it's just fun to figure out these types of problems because finding dm is truly the hardest part. And having the ability to conceptualize and understand what can be represented as a function of something else is really important, and it will help you in more than just physics. It will help you in literally anything, because truly life is about analyzing data, and this is essentially analyzing data. You're taking a cylinder and you're trying to see, how can I make a function out of this, or how can I find mass as a function of r. So I hope you enjoyed. I hope you guys got something out of this video. I plan to post more, and I hope you guys have a great day. I'll see you guys next time.